We'll explore 1010 Data's transformational query language, how to optimize queries, and how to use the strengths of the language to reduce complexity. Before going into detail on 1010 Data's transformational query language, we'll explain the term transformational. In SQL, you describe the desired result, but don't indicate how to get to it. The DBMS system figures out that path, taking your declarative description of the result set and producing a query plan to reach that outcome. 1010 Data's native query language is transformational. The developer describes what to do to get the final result, not what that result is. A 1010 Data query consists of operations called actions, with each transforming the result of the previous action. The first action is applied to the original table to produce a new virtual table. The second action is applied to the result of the first action, producing another table. That result is then operated on by the third action, and so on. This approach meshes with an analyst exploratory workflow. When working with the billion-row dataset for the first time, you'll need to perform analysis to understand the dataset's dynamics. You'll run exploratory queries and test what-if scenarios. You may not know what the result is, so attempting to describe the query can be difficult. A transformational query language allows you to express your analytical query as how you'll think through the problem, step by step, with each step building on the prior. 1010 Data calculates results using lazy evaluation. While each action modifies the table, the platform may defer calculations which do not impact the result. Specifically, the values in a computed column defined in a Willbe are not calculated until the column is referenced in another action or the displayed result. Willbe is the query language element for creating a new column. In linking, columns linked in from another table may not be resolved and linked until they are referenced by a subsequent action. Here's an example query. First, a Willbe statement creates a column named myColumn. There's then a selection on a field named otherColumn where the value equals 100. Finally, there's a selection on the myColumn field we created in the first step where the value is greater than 50. To see the impact of lazy evaluation, let's remove the last line from the query and replace it with a callWord statement which hides the myColumn field. The callWord function allows you to show or hide columns. We still have the Willbe for myColumn, but it's not referenced or displayed in the result. The third line containing the callWord hides the myColumn field. Since there are no references to myColumn, the platform doesn't calculate this field. Lazy evaluation skips over calculations not referenced, but it can also reduce calculations even when the column is referenced. Let's go back to the original example. Here, we see our final selection where myColumn values are greater than 50. This occurs after we select otherColumn equals 100. Imagine the table has 1 billion records, where otherColumn equals 100 includes 100 million records. The myColumn greater than 50 selection only applies to those 100 million records. The system takes advantage of lazy evaluation to only perform this calculation on the subset of records applicable at that point in the query. The other 900 million records are unreferenced and therefore untouched.